All right, the chapter makes a pretty drastic shift, at least in my mind. It makes a drastic shift here in the second half of chapter 3. It's kind of related because we're going to get into moles in just a minute, but it's also quite different because it's a whole new subject here, talking about solutions. So we're going to talk about solutions and solution concentrations and dilutions and things like this for the rest of the chapter. The first thing we need to figure out, though, is what is a solution? Now, I bet in your mind you have at least a thought of what a solution is, but we really need definitions for things like this. As scientists, we want to have a definitive definition that everyone agrees this is what a solution is. And so our definition of a solution is a homogeneous mixture of two or more substances. Now, in your mind, I bet you were thinking of a solution being like a mixture of two things, and probably the thing that you pictured was having relatively equal amounts, probably in the same phase. And while there are plenty of solutions that would fall under those different categories like that, there are lots of solutions that wouldn't. There's actually a lot of solutions that are formed from two different phases, where you have maybe a gas dissolved in a liquid, or a solid dissolved in a liquid, or technically even solids in the gas phase. Smoke is technically a solution because you have tiny little solid particles that are evenly distributed in a gas in the atmosphere. So there's lots and lots of different kinds of solutions, but every solution is going to have at least two parts. It's going to have a solute, which is the minority, that is the thing that is dissolved, the thing you have less of, and then you have the solvent, which is the majority, and that's the thing that is dissolving the solute. We do not care what they are made of. All we care about is which one is there more of, which one is there less of. The thing that we have more of is the solvent. The thing that we have less of is the solute. The majority of the time, our solvent is going to be water. Doesn't have to be, though. There are plenty of situations where you will have water in a solution, and the water is actually the solute. You actually have less water than the other thing. For example, there's plenty of alcoholic beverages. Things like rum and like I believe Everclear as well. There's some plenty of alcoholic beverages where actually there's more ethanol, there's more alcohol than there is water in the drink, and so that would not have water as the solvent. That would be water as a solute. So just a few other examples here of solutions. You can have gaseous solutions. So this is where you have a gas dissolved in another gas. The atmosphere is an example of that. In that case, nitrogen gas is our solvent, and oxygen, CO2, argon, all the other gases, water vapor that's in the air are solutes, because we can't have more than one solute. We can have tons and tons of solutes, but we can only have one solvent. You can have lots of things that are in the minority, but you can only have one majority. You can have liquid solutions, so you could have a gas dissolved in a liquid, so soda pop, as some people call it, or just pop, or just soda. Any carbonated beverage like that is a solution, because you actually have a gas dissolved in a liquid. That's why when you open up the can of pop, the bubbles start to form because now they're able to escape. When it's sealed up, they have nowhere to go, and so they just stay in the solution. But as soon as they're open to the atmosphere, the gas starts to come out of solution, and then eventually you have a soft beverage, which is nasty. You can have liquid solutions, so vodka, like I said, gasoline. You can have solids dissolved in liquids, so salt water, the ocean, is actually little particles of things that, if they were not in solution, would be a solid. It's kind of debatable as to say they're actually solid particles in the water, but it is considered a solid in liquid solution. And you can even have solid in solid solutions. Any kind of metallic alloy is considered a solid in solid solution. We have one solid that has dissolved another solid. All right, when we're talking about these solutions, it's useful to think about them in terms of the concentration of the solute, how much solute you have. And so you're probably already familiar with these terms, but we say that a dilute solution is any solution that has very little of the solute. So a dilute, you could think about it in terms of it has been diluted. You have a lot of the solvent, not very much of the solute. This is what happens to your drinks when you go to a fast food restaurant and you don't specify that you want them to go easy on the ice, and so they fill your cup with ice, and 3 minutes later it tastes terrible because the ice has melted to the point where it's watered everything down. It's diluted the drink. So a dilute solution, I'm only a little bit bitter about that, by the way. A dilute solution has a small amount of the solute compared to the solvent, whereas a concentrated solution has a large amount of the solute compared to the solvent. Now, you will never have a concentrated solution where you have more solute than solvent. It is literally, definitionally impossible. Because if at some point what was the solute, you've added enough of that you actually have more of that now than you have of the solvent, well then now that's the solvent, because it's now in the majority. So definitionally, you will never have more solute than solvent. It is definitionally impossible. Because we don't care what the molecules are, we only care how much of them are present, how much is present. So as soon as that molecule has more of it and its buddies around than the other molecules, then now it's the solvent. So dilute, relatively low amounts of solute; concentrated, relatively large amounts of solute. All right, if we're going to quantitatively describe how much of those solutes are present, there are lots of these different units that can be used to describe it, but by far the most common one that chemists use is molarity. And arguably, molarity could be the most common unit used by chemists, just period. Like, it's possible we might even use it more than mass or more than moles. Those would be the closest ones probably, but I would make the argument that molarity might actually be the most common unit used by chemists, just because we do things in solution a lot. The majority of the chemistry that we do happens in solution, partially just because it's relatively easy to control it when it's in solution. Everything is very well mixed together. Lots of stuff can dissolve in water, so there's multiple reasons for it. But molarity is for sure the most common concentration unit that chemists are going to use. This is a very, very important unit. And so what molarity is it is simply the number of moles of solute in a solution divided by the number of liters that the solution is occupying, the volume that the solution is occupying. So it is moles per liter. The total number of moles for that particular solute in the solution divided by the number of liters that the entire solution is occupying. So, just to do a quick example here, and I believe, yes, I do have a spot where we can do it here. So, what is the molarity of a solution made by dissolving 13.6 grams of sodium hydroxide into 500 mils of solution? So we have a couple bits of information given to us. So we know we have 13.6 grams. We know that we're working with sodium hydroxide. And we know that we have 500 mils of solution. Now we also need to keep in mind that the molarity is the number of moles divided by the liters. And molarity, by the way, is signified by this uppercase M, capital M. It is not lowercase m, because that's mass. So we don't want no lowercase m. It is uppercase M is molarity. So if we're trying to find the molarity, if this is our goal, the molarity here, then we need the number of moles and the number of liters. We need to find those two things. And this is always going to be the case when we're solving questions like this. If we have a three-part equation, we're trying to find one of those things, well then we need to find the other two. That's always going to be our goal here, is to find the other two. So in this case, we're trying to find the molarity, so we need the number of moles and the number of liters. Now the number of liters, pretty straightforward. We're told we have 500 mils. You could probably do this in your head, but just to show you the process here, we're just doing a simple unit conversion. If we have 500 mils, we need to convert that to liters. If you go back and look, there are 1,000 milliliters in 1 liter. So those milliliters cancel out. Can't speak today. And that is going to leave us with 0.5 liters. Which actually, just because I don't want to have only one sig fig here, I'm going to change that and say that I have 3 sig figs there. You're not allowed to do this, but I'm the professor, so I can do what I want. At least for practice problems like this, not in everything. In these practice problems, I have absolute power. So I'm going to go ahead and give myself 3 sig figs there. So I have 0.500 liters. So that is my volume. To find the number of moles, I need to take the mass that I'm given and convert that to moles. So I have 13.6 grams of sodium hydroxide. And if I look up sodium hydroxide in the periodic table, I believe it comes out to 40, if I remember correctly. So sodium on the periodic table is 22.99, oxygen is 16, and hydrogen is 1.008. And so it's essentially 40. I'm just going to go ahead and round it to 40. I'm getting 39.998. I'm just going to round that to 40. So I'm going to say there are 40.0 grams of sodium hydroxide in every 1 mole of sodium hydroxide. And so if I go ahead and do that math, 13.6 divided by 40, that is 0.34 moles. So now I have the moles, I have the liters, and so the molarity is 0.34 divided by 0.5, which is 0.68 molar. Again, that's moles per liter, or just molar. All right. I want you to try this one on your own before I work it out with you. So this one is a little bit different, but not much. You're essentially just trying to find a different part of that equation. Remember, the molarity is the number of moles divided by liters. And this question is asking how many grams of Kf are in 2 liters of a 0.24 molar Kf solution. So go ahead and try to work that out on your own. Pause the video and then come back and we will work it out together. Okay, I hope you paused that and tried to work this out. So we're trying to find the mass. Now, if you notice, there's no mass anywhere in this equation. There's molarity, there is moles, and there is liters. But the number of moles is just one step, one conversion away from the mass. So if we can get the number of moles, we can do a mole to mass conversion and get the mass. So what we're trying to find here at the beginning is the number of moles, and then we'll go from there. The other two parts of the equation are just straight up given to us in the question. We're told what the molarity is, and we're told what the volume is. So we can just go ahead and plug those in here. So, and actually, don't need to write m again. So the molarity is 0.24 molar. That is equal to N, which is what we're trying to find, divided by 2 liters. So I'm going to multiply both sides by 2 liters. That will give me N is equal to, and by the way, the molarity here, that is moles per liter. And so when we multiply the liters by the moles per liter, those liters are just going to cancel out, leaving us with moles. So that is going to be 0.48 moles. So we have almost a half of a mole of potassium fluoride. And so then the last thing we need to do here is we need to go ahead and convert 0.48 moles into grams. And so if I look at the periodic table for the molar mass of potassium fluoride, potassium is 39.1, fluoride or fluorine is 19. So I have, for every 1 mole, I have 58.1 grams. So my moles here cancel out. So 0.48 times 58.1 leaves me with 27 point, and let's see, I only get 2 sig figs. Oh, that hurts. But we'll go with it. So actually, the calculator gave me 27.888, but with proper sig figs, that would just be 28 grams. Because we would cut it off here. The next digit is 5 or greater, and so it would be 28 grams. All right. I think we'll go ahead and pause or stop the video here. This one is kind of a little bit long again, but we'll pick up with the next question here in the next video. Still talking about molarity, and then we will get into making solutions and solution dilution, which is also a very important topic. So I'll see you in the next video.